Hey class, Mr. Moyden here with a video to help launch our new unit after leaving the world of the coordinate plane and distance and midpoint, returning back to the Euclidean plane and introducing the idea of logic and reason to make geometry a little more rigorous. So we're going to start that with conditional statements. So what are they? Another term for a conditional statement is an if-then statement. So it comes in that form typically. It's preceded with if, and of course the word then appears in there somewhere. It includes a hypothesis, which is the part that follows the if. So if it follows if, you're dealing with the hypothesis. And the conclusion is what follows the then. So the then, the stuff that comes afterward, is the conclusion. Typically, in terms of logic and reason, we associate the following I don't want to say variables exactly, but the following symbols in the letters to indicate hypothesis and conclusion. We usually give the hypothesis a label of P and conclusion a label of Q. Now this seems very abstract and very broad right now, hypothesis, conclusion, why do they have their own symbols, if and P and Q? It'll make a bit more sense in the following concrete example. So let's look at one that's not mathematical, just to wrap our heads around what a conditional statement is and break it apart into its real underlying meaning. Here's one. It says, if it is a cat, then it has whiskers. So think about that statement just as it is, what it's saying, what it's not saying, whether it's true, whether it's false. We'll get to all that in just a moment, but let's break it down. This portion right here, of course, would be called the hypothesis. I'll just abbreviate. And this portion over here would be the conclusion. So you could think of this statement as visually being summarized or symbolically summarized as P implies Q. So how do you pronounce what's written here? Let me write that. P implies Q. If it is a cat, then it has whiskers. The catness implies the existence of whiskers. So thinking about your own experience in the real world and interacting with animals and such, of course, you know that this is a true statement, right? The truth value of this is true. Now, again, this may seem elementary. We're going to play around with this statement and sort of reorganize it and break it apart and try and figure out if we can take these pieces and come up with things that are not necessarily true, even though they're composed of the same parts. So let's take a look at sort of a different formulation of these same pieces where you have a cat and you have whiskers. This symbolic notation here is indicating what we're going to do. It says Q implies P. So going back a slide just for a moment, P essentially was the cat part, right? And the Q essentially was the whiskers part. So this statement would read, and I'll have to abbreviate just because my writing is not so good on this tablet, if it has whiskers, so if whiskers, then it is a cat. Right? Again, I'm just leaving out some words just because of space's sake, but if it has whiskers, then it's a cat. That's what this Q implies P is essentially conveying, right? So the two parts of the statement have been switched around, and for that reason, we call this kind of statement where you take the original and reverse it, we call this a converse. This is called the converse. So notice that much of the grammar of the original, and I have the original up here on the very top, remains the same, except for the fact that the hypothesis and the conclusion have essentially switched places. If it has whiskers, then it is a cat. Now let's think about, once again, the truth value of this statement. Is this actually true or false in the real world? Well, if it has whiskers, does that imply that it's a cat? Well, no, this is a false statement. For example, dogs have whiskers. You could say that mice have whiskers. Certain kinds of catfish could be considered as having whiskers. So this is a false statement, and those examples that I gave of certain kinds of dogs and mice and such, those are or what are called counter examples. So I'm not going to define this word because it's sort of self-explanatory. Counter means to go against. So it's an example that sort of explains or demonstrates why a statement is false. If it has whiskers and it's a cat, it's false because of the existence of these counterexamples. Playing around with this some more, we've reversed it. P implies Q has become Q implies P. That's called the converse. let's take a look at another reversal of sorts. Squiggly P implies squiggly Q. Now the squiggle there has its own meaning to it. Let me give myself a bit more room. We pronounce this symbol, which is in English we call this symbol a tilde, but these two symbols mean not. Or negation is another way of verbalizing that. So not P implies not Q. So how does that look like in terms of this actual statement? That would read, once again I'll abbreviate, if not cat, then no whiskers. So notice that we've maintained the overall order. Catness comes first and whiskerness sort of comes afterward, just like in the original at the very top. But we've added, of course, the idea of negation. We've added the negative portion of it. Not P implies not Q. So looking at the statement again in terms of its actual meaning, what is it trying to convey? We know what it says. Actually, I haven't given this a name. Let me pause and do that. So the last one was called converse, right? When you keep the order but negate both the hypothesis and the conclusion, we call this type of statement an inverse. An inverse. So contrast that and compare that to the converse. The converse simply switches. The inverse keeps the order but negates it. Now, in terms of whether or not the statement is actually true, right, we have to think about what it's actually saying. If it is not a cat, then you need to meet that condition. So, for example, let's talk about a dog. So if it's not a cat, let's say it's a dog, then you meet the condition. The question is, does the conclusion actually match that? If it's not a cat, then it has no whiskers. Well, a dog meets the first part, but it fails the whisker test because a dog could have whiskers. So this is an example, once again, of a false statement. Now, is the inverse always going to be false? Not necessarily, as we will see in class. Looking at the final example here, we have the following symbolic notation. Not Q implies not P. So just so I don't forget, what is this thing actually called? This is called the contrapositive. Very fancy sounding term. The contrapositive. What would that look like in this example? Well, notice that we're doing two things. We're switching the order, Q and P, and we're also negating. So this would read, again abbreviated, if no whiskers, then not a cat. If it does not have whiskers, then it is not a cat. So once again, notice several things happening here. We've negated it, but we've also switched the order, right? The original statement up at the very top, the Q and the P have switched places. If it is not a cat, if it has no whiskers, then it is not a cat. Well, if you really think about what the statement is actually conveying, what it's saying, this is a true statement, isn't it? The initial statement was true. If it's a cat, then it has whiskers. Well, if it doesn't have whiskers, that means it's not a cat, right? Because the cat aspect of it implies the existence of whiskers. So in the absence of whiskers, or not Q, then you can conclude that it will not be a cat. So again, a very simple, non-mathematical idea in terms of this basic example of cat and whiskers, but you can really start to analyze logic and in terms of what is a statement really trying to convey and what does it mean to be true and what does it mean to be false. You can start to wrap your head around these bigger ideas by dealing with a simple statement. So let's close with an actual example of the kind of questions you'll see in the near future. So here's a conditional statement here in pink. This one's actually mathematical. If two angles are vertical angles, then they are congruent. So the question that accompanies this statement is write the converse and determine if it's true or false, and if it's false, provide a counterexample. So remember, there's basically four formats that we've learned, just to review. We've learned four orders, you might say, of conditional statements. You have the original, which comes as P implies Q. You have the converse, which is Q implies P. You have the inverse, which is not P implies not Q. And you have the contrapositive, which is not Q implies not P. And since you want the converse, this is the one that's called the converse. So what would that sound like in terms of the actual phrasing in the statement? That would say, if, again I'm abbreviating, if not congruent, then, whoops, getting ahead of myself. If congruent, looking for the converse, if congruent, then they are vertical angles. Right? The converse simply switches the order, and that's exactly what I've done, albeit in abbreviated form. If they are congruent, then they are vertical angles. Now the question is that actually true or not? Well, let's think about it. If you have two angles that are exactly the same size, do they necessarily have to be right across from each other in a vertex form? Well, oops, let's see. For example, if I were to draw this rectangle, here are two angles that are congruent in that they're both 90 degrees, but they don't share a vertex, do they? Right? Remember, vertical angles are angles that are sort of in this configuration, right? That's not what we have here. So looking back at the converse, it said, if they are congruent, then they are vertical angles. Well, this is a counterexample, so that statement would be false. And the picture that I drew, which I don't have room for here on this slide, is the counterexample. So a lot of information, a lot of new vocabulary. Statement, converse, inverse, contrapositive are the most important ones, I would say. So with all this information in mind, I'll see you in class. Hope this helps.